Now I promise this really is your last mini lecture for OChem 1 lab. This is a new addition to the OChem 1 lab because we had a grant to purchase a small NMR spectrometer. Now you're going to learn about NMR spectrometry in great gory detail if you take OChem 2, but it's such an important technique and such a great complement to IR that you're going to use it in your pet molecule. So this is just kind of a big shallow overview to help you use NMR to identify the identity of your pet molecule. So you've already looked a little bit at spectroscopy. It's all about electromagnetic radiation, energy that somehow or other interacts with matter, including molecules. And in IR, we've seen the energy level is kind of middle of the road, right in the middle of the electromagnetic spectrum, more or less. Now in NMR spectroscopy, we're looking at a much lower energy level, looking at radio waves, a really teeny tiny energy transition as this region of the electromagnetic spectrum interacts with your molecule. What's happening? Well, in IR we know that the energy causes the bonds to kind of stretch and bend. In UV-Vis it's a much higher amount of energy, and it actually kicks an electron from a lower energy orbital up into the LUMO. And now in NMR it's just a little teeny tiny transition called a spin flip. And we'll save the details to 2302. But what's important is that when the frequency of that radiation matches the energy gap, the molecule absorbs the energy, and you see an absorbance somehow or other, and it records a spectrum. And from that spectrum we get all kinds of information. In NMR, and this is why it's so complementary to IR, it tells us information about the carbon and hydrogen skeleton, which of course IR is pretty useless for. So this is what it looks like. This is a proton NMR spectrum. What you can see along the bottom is the typical range is from 0 to 10 parts per million. Parts per million is the units of NMR. And what it tells us, many things. Number 1, you can see we've got 1, 2, 3, 4 sets of signals. That tells you more or less how many different types of hydrogens are present in your molecule. Note too that those signals are in completely different regions of the spectrum. Are 1.3 parts per million, 4.3 parts per million, and these are both down around 7 and 8 parts per million. We'll use a correlation chart, just like IR, to determine what that's telling us about the environment these hydrogens are in. You see these squiggly lines here. These little squiggly lines above each set of peaks are called integrals for obvious reasons, and that tells you how many hydrogens are associated with each set of signals. You also undoubtedly are noticing that looks like 4 lines. This looks like 3 lines. It's not just any 3 lines, they're in a ratio of 1 to 2 to 1. Those patterns are really important, and they tell you a lot about how the molecule is put together. And finally, the gap between the signals is important, but we're not going to get into that in 2311. So first off, why do these hydrogens appear at different parts per million? So the symbol delta is the abbreviation for parts per million. It's called the chemical shift. It's where things appear. And the reason hydrogens appear at different chemical shifts is because they're in different environments. The 3 hydrogens of this methyl group are in a completely different environment than the single hydrogen that's next to the chlorine and the oxygen. Wow, that's really next to some electronegative elements. This hydrogen, my gosh, it's attached to an electronegative element. So these hydrogens feel different amounts of electron density, and as a result they show up at different regions of the NMR spectrum. Now, here's an aromatic ring. When you get out your correlation chart and use the correlation chart, for example, in Morrig or Cardi, either one's fine, you'll see that these hydrogens all show up really far to the left. Okay, so the typical region for aromatic hydrogens is around 7 to 8 parts per million. So if you have signals around 7 to 8 parts per million, you know you have an aromatic ring. What's also interesting about this particular example is that we have 6 hydrogens that are absolutely identical. They're in identical electronic environments. We could even say we know that because it's a very symmetric molecule. So when it comes right down to it, we could identify in this molecule that we have 3 different kinds of hydrogens. Actually 4. The hydrogens on the methyl groups are all in the exact same kind of environment. The hydrogens labeled B are close to the methyl groups, but they are not in between the methyl groups. That's hydrogen D, and so on and so forth. So basically what this is saying is I would expect to see 4 sets of signals for this molecule. Well, it turns out it's not going to be true, that all of these aromatic hydrogens pretty much show up on top of one another. But by symmetry, we'd expect 4 different sets of hydrogens. So NMR tells us a ton of information about the carbon-hydrogen skeletons put together. It tells us not only how many different kinds of hydrogens there are, it tells us how symmetrical the molecule is. The integrals tell us the number of hydrogens associated with each signal. And we'll see, too, that the pattern tells us how many hydrogens are adjacent to one another. So here's an example of a typical NMR spectrum. So when you see this, the first thing you can do is think about the number of sets of signals. Well, this one clearly has 1, 2, 3 sets of signals. So that means I have 3 different kinds of hydrogens in my molecule. Then you can look at the integrals, and it's a simple whole number ratio. You just measure this distance from here to here, and that is relative to the number of hydrogens associated with each signal. Well, what I can see is that this one is about 2/3 the height of this one. So, let's see. I would say then that if this is 3 hydrogens, this one is also 3 hydrogens, and this one is 2 hydrogens. Okay, now I don't know if that's right. This could be 4 hydrogens to 6 hydrogens to 6 hydrogens. But what is certain is that since these 2 integrals have the same distance from bottom to top, then that means this signal and this signal are representing the same number of hydrogens. And this one over here is 2/3 that number because it's about 2/3 the height of those integrals on the right. All right, then you can start paying attention to where these things show up. So it turns out that things that are down around 1 are just plain old methyls and ethyls and things like that, plain old hydrocarbons. Things further down around 4, they're usually in an electronic environment that is a lot more like a carbon bearing hydrogens next to an oxygen. So maybe a CH2 or a CH3 next to an oxygen. If you look at your correlation chart, this guy is a dead ringer for a methyl group next to a carbonyl. So your correlation chart is going to tell you what kinds of functionality is in the neighborhood. And of course your IR is going to be really useful for that. And then finally, the patterns are really helpful because they tell you how many hydrogens are next door. So if this is a 3 hydrogen signal, and this is a 2 hydrogen signal, and this is a 3 hydrogen signal, you can see that this is just one single peak. That's called a singlet. The n+1 rule says your signals are going to be split into a number of peaks based on the number of hydrogens adjacent. So if I have 0 hydrogens adjacent, then my signal should show up as a singlet, 1. So that's telling us that this signal for 3 hydrogens has no hydrogens next door. So that really makes sense if this is what we're talking about, because there's no hydrogens next door. Well, what about this guy? There's 4 signals there, so that implies that whatever this 2 hydrogen signal is, here's my CH2, it must be next door to a CH3, because that CH3 plus 1 gives us 4. So 3 adjacent hydrogens plus 1 gives us 4. So this is just helping me build up this molecule as a CH2 next to a CH3. Wow, that's a lot of information. And this guy a triplet? Well, that means if this is a 3 hydrogen signal, as in a methyl group, it must be next door to 2 hydrogens, because 2 plus 1 is 3. Well, just to tell you what this molecule is, since I'm sure you're dying to know, this is ethyl acetate. Where the CH3 from my carbonyl is right there. The CH2 next to my oxygen is pulled way to the left because that's a completely different environment. And the methyl group next to the CH2 is that guy down around 1. So you're not going to, we're not expecting you to master NMR, but you can get the basic principles on how you can use NMR to figure out exactly what pet molecule you have. And we will be giving you a list of possibilities, so that will make it a lot easier. But let's just go through a couple of examples here. This guy is adjacent to no other hydrogens. They have to be right next door. So this would be a singlet. These two are next door to the CH3, so that would be a 4-line signal. And these guys are right next door to 2 hydrogens, so that would be a triplet. Then how about this guy? Well, none of these are adjacent to any hydrogens. Remember, it has to be on the carbon right next door, and the carbon right next door has no hydrogens on it. So all 9 of those hydrogens are going to show up as a singlet, and they're all absolutely identical. They're all in the same exact chemical environment. So I'm going to see a big 9 hydrogen singlet, and if I look up my correlation chart, this is going to be pretty close to 1, maybe 1.2 or so parts per million. These guys, well, who are they next door to? 2 hydrogens. So that's going to be a triplet, and that's going to be down around 2 if you use your correlation chart. So that's going to be 2 hydrogens. And then this guy, okay, back to now looking at this one, it is adjacent to 2 hydrogens as well, so it too should be a triplet, and we'd have to use our correlation chart to figure out where that one is. But so we'll have 2 two hydrogen triplets. And since we have our IR as well, yay, we know there's a ketone in there, so we can piece everything together and figure out just exactly what molecule we have. Much, much, much more information than a melting point, boiling point, or TLCRF. So, this link takes you to an online database of just about every molecule you could possibly want, and you can look up the NMR on these particular spectra, on this particular database. It's super, super helpful. You just have to agree to agree to the disclaimer and use this database. You can put it in by compound name or molecular formula, and you can look up all kinds of information. So, very, very useful information. So that pretty much wraps it up. For your PET molecule, like I said, we'll give you a list, but you have your IR, most of you do anyway. Analyze that first, figure out what kind of functionality you have, and I'm definitely going to be checking in with you about this. Think about your solubility test. Does that correlate? And then for the NMR spectrum, you're going to go through it very systematically. I'm going to help you. And then finally, you can check the spectral database to see if it is a match. So that's it for NMR and your PET molecule, and we will see you in lab.